So how do Euler's method, improved Euler's method, and RK4 match up? Well, let's go ahead and look at a real-world example. We'll kind of build a different type of model here known as a tank or compartmental model. And in this particular problem, let's suppose we have a tank of water, and it has water flowing in at a rate of 10 gallons per minute. Okay, so down here I already have the kind of the rough, what we call the box diagram version of this problem set up down here. You could draw it as fancy as you want, but it's basically a box into which we have something flowing. We have water coming in at 10 gallons per minute. And I'm just going to denote that as 10 gal over 1 minute. I always like to write rates like this in the fractional notation. You can clearly see the units. And also coming in is a concentration of 10 milligrams per gallon of chlorine. So every gallon that comes in, there's going to be 10 milligrams coming in with each 1 gallon. So write that down. The chlorine water exits the tank at a rate of 10 gallons per minute. Okay, so we know that the same amount of water that's coming in is also coming out. The tank is initially clean of chlorine and contains 50 gallons of water. Okay, so that's going to remain the same, right? Because if you're pumping in 10 gallons per minute, but you're also draining 10 gallons per minute, then your net change in water is 0 gallons per minute, right? So if I'm filling up a tub at 10 gallons per minute, but I'm draining it at 10 gallons per minute, however much water was in there to begin with will always be the same amount. Now, one of the things that we're going to assume in this model as we build this differential equation that we're going to then analyze with these three methods is going to be in milligrams per hour. Right? Because Y is going to be measured, we're going to try to keep track of how much chlorine is inside of here as a function of time in minutes. Now, one of the things that we're going to assume, and you have to assume this, it isn't the most practical assumption, but as that chlorine water comes in, we have to assume that it is well mixed, that it is basically always being stirred at all times, right? That basically, of course, what comes in will sort of float on the top for a while, but we're just going to assume that this is constantly being stirred. So imagine that there's some stirrer in here that is constantly stirring it so that basically all of that chlorine that comes in is already well mixed the instant it hits inside of the tank. Now, in order to generate this dy dt equation, because that's in milligrams per hour, we have to think in terms of how many milligrams are coming in each hour minus the number of milligrams coming out each hour. At first, it may be tempting to say, well, isn't it going to be, well, if there are 10 gallons every minute and there's 10 milligrams in every gallon, then every minute, if you look at the units here, you multiply these, well, gallons would cancel out, and that would give you 100 milligrams per 1 hour, right? That's what we want to know, how many milligrams are coming in each hour. And so, well, isn't that exactly what's coming out then? And the answer is no, because those 100 milligrams are mixed into 50 gallons, right? And only 10 gallons of that liquid is coming out. So some of that original chlorine stays in there. And meanwhile, more is being pumped in, and then more is being drained out, and more is being pumped in, and more is being drained out. Everything is being well mixed. And so you can't assume that what comes in is what goes out, right? So especially since it becomes diluted equally within this water. So in terms of what's coming in, we have to convert into the units that we want for our dy dt. In this case, 10 gallons for every minute, 10 milligrams in every gallon. Well, if there's 10 gallons coming in, that means each of them gets 10 milligrams. So there's going to be 100 milligrams being pumped in each minute. Oops, I wrote hour here, but I meant to write minute. All right. With that said, we now need to think about what goes out, right? This is going to be 100, and I did hours here as well, excuse me. Hours, we should be in minutes. We could convert to hours, but, why would we do that? Now, what's coming out is 10 gallons per minute, but we need this to be in milligrams per minute, and if we kind of follow the same structure here, in order to go from gallons per minute to milligrams per minute, we would have to multiply this by milligrams over gallons, right? In other words, we need to know what is the concentration. By the way, this is called the flow rate. That's how the fluid is flowing, and this is what we call the concentration Concentration is how much mass you have per volume. And we know that inside of this, what's coming out of this tank is what's inside of it. So we need to figure out what's the concentration inside of the tank. Well, it's going to be something dissolved in 50 gallons, right? Because what goes out is based on what's inside. And how many milligrams are inside of that at any given moment? Well, we don't know that exactly, because if we did, then we wouldn't need to write a differential equation. We would just know y as a function of time. But we have a variable that keeps track of that for us. The amount of chlorine in the tank, which is y, in milligrams after t minutes. Simply put, that's going to be y milligrams that are going to be dissolved in 50 gallons. And because that's always changing at any given moment in time, all we know is that it's going to be y milligrams. Okay, look at the units here. Gallons cancel out. You've got milligrams per minute. Multiply the top, 10y. It's milligrams over 1 times 50. That's 50. And that's in minutes. And if you want, you could even simplify this a little bit further, which I'm going to do. 10 over 50 is 0.2. And I just like writing 0.2y. It's going to be a little bit easier to input this as we go to do our Euler's analysis. So here's my differential equation. And my initial condition, we're told that the tank is initially clean. So y at time 0 is 0. There is our initial value problem. IVP. And now let's go on to analyze it. So I'll pull up the technology in just a moment here, but here is what we would generate with Euler's method. And keep in mind that we don't know the solution. I'm going to write that. We don't know the exact solution. Now, we could get the exact solution because this equation is actually separable, but let's just see if we could try to figure out what we believe the right answer is without having to know the solution, because, well, that's why we use this method, because we don't have the exact solution. So with Euler's method, with a step size of 1, we'd get 400 at time 10, which is the time at which we wish to estimate how much chlorine is in the tank after 10 minutes. Well, we have our differential equation, we got our initial value problem. Let's say we don't know how to solve this, because oftentimes we won't know how to solve an equation if we're resorting to these numerical methods. By the way, if you can solve the differential equation, there's no sense in doing the numerical methods because there's a more exact answer available. In fact, it is the exact answer. With Euler's method, a step size of 1, we get 446 milligrams of chlorine at time 10. With 0.1 step size, we get 434 milligrams. And you can see that there's a relatively big jump, right? From 446 to 434. Not tremendous. In a lot of cases, this could be more dramatic, but for this example, because our differential equation is pretty stable in terms of the rates of change generated, we're not going to get, huge changes in Euler's method. But look at improved Euler's method. For step size of 1, we get 431. And if we decrease that step size by a factor of a tenth, or by a factor of 10, then we get 432. And you can see that that change is a smaller change than here. Now, with RK4, I just wanted to generate for a step size of 1 and 0.1 and 0.01. And the thing that I want you to notice is that we're accurate, even at a step size of 1, we're precise to the hundredths place. Right? In other words, we know that if we decrease the step size, we're getting more accurate. But look at the amount of accuracy that's gained here. It is not tremendous, right? And so with a step size of 0.01, we're not even noticing a difference to 3 decimal places for the step size of 0.1. So let's pretend we don't know the solution. How do we gauge whether we're converging in on the right answer? Well, you probably already guessed it. If the answer isn't changing by much anymore, then that means that we are converging probably to what could be considered the most correct value of chlorine at time 10. Now, in order to actually get an error analysis without an exact solution to compare to, compute the error between step sizes, where the larger step size y value is the approximate, and the smaller step size y value is the exact. So if I think about this situation here, and I did an error analysis, and I'll just say from delta t equals 1 to 0.1, the way I would compute this is I would take, well, again, we're going to treat the exact as being the one with the smaller step size, right? Because that's a better estimate. We know that. The approximate in this case would be 446 minus 434, and then multiply that by 100%. Now, that difference, of course, is we know that we're above, right? That this 446 is bigger than, which is why we get positive 12. And if we divide that by 434 and multiply by 100%, 12 divided by 434, that'll give us an error of approximately 2.8%. Not bad. Really pretty good, right? But we could do better than that. You can notice that now we're a little under where we should be. And the percentage error here would be the approximate, the 431, minus the more exact of the two, divided by the more exact of the two, times 100%. You can see that we're going to be pretty darn close here. In fact, our error now is about negative 0.2%, which is, of course, much closer to the exact answer. The change is much smaller here. Right? Now, you can even tell with Euler's, if we assume that with RK4, we expect about 432.33 milligrams at time 10, then you can see that, with not that far off from that exact value, but we get much better with improved Euler's, and we get much, much better with RK4. Now, let's just we don't want to compare typically the largest to the smallest. We usually want to compare them adjacently. So the error here, what I want you to notice, would be the more approximate, 432.330, minus the exact. Again, it's not the exact, it's just the more exact of the two, divided by the more exact of the two, times 100%. And that's going to come out to, let's see, I notice a difference of an increase of about 0.002. So we'll have negative 0.002 divided by 432.332 times 100. Well, that actually comes out to negative 0.0004%. In other words, by decreasing the step size by a factor of 10 using RK4 in this particular example, our precision did not increase that much. We got a little bit closer, right? But here, if you notice, to 3 decimal places, the error is going to be 0%. The relative error from the less exact to the more exact, right? In this case, the less exact would be the 432.332. The exact would be the 432.332. To 3 decimal places, we have 0% error. So we might conclude at this point that that our answer we expect at t equals 10 minutes to have 432.332 milligrams of chlorine in the tank. Now, you normally would just jump straight to RK4. We're just trying to do a comparison here because this is kind of the easiest, and this is kind of the hard, right, as far as computational concern goes. But we've worked through this progression to see that you could make some small changes, add more slopes, and average them together, and the more slopes you get, the more precise your answer will be. And then, once we're using RK4, let's just say that's our focus using RK4, well then the only way we could get error estimates is by, basically decreasing the step size until visually the change is not noticeable to as many decimal places as we want it to not be noticeable to. If you just wanted it to the nearest milligram, well then going from step size of 1 to 0.1, you'd say, all right, there's no change there to the nearest milligram, and therefore I would estimate 432 milligrams. But you could keep decreasing the step size until you see stability in as many decimal places as you want. Let's say you needed 5 decimal places of stability. Well, then you'd get 2 more decimal places here and then compare them. Let's go ahead and just jump over to the app real quick. And the way I generated these answers was, okay, here I put my differential equation in. Just want to make sure that our graph goes to time 10. In this case, because I plugged in my initial point of 0, 0, 0, right? I needed to make sure that I could actually see the graph peak out here at time 10. So for us, that turned out to be, I had to keep increasing this y value until I could see the red graph, put in my initial condition first, and then 0, 600 was a lot higher than I needed. But there it is. And now I can change the method. Right now it's set to RK4, but if you go to Euler, there's our Euler estimate at time 10. Here's your improved Euler estimate at time 10, step size of 1. And by the way, if you want to see all those slopes, y1 prime and y2 prime are what we call k1 and k2. And then the delta y, the change in y, is the average of 100 plus 80 divided by 2 is 90. And that's the information that we can gauge from that. Now, if I wanted to go to RK4, by the way, you see it's called the Hoon method. That's another name for improved Euler. I believe that's the individual credited with it. Switch to RK4. You could expand that table out here, and you could actually see the 4 slopes. And if you take K1 plus 2K2 plus 2K3 plus K4 all divided by 6, that'll give you the 90.6633. And then you can see here's the time 10 estimate. When you decrease that step size, then you would just want to make sure that you go down to time 10 so that you can see, we don't need all these other columns. There's our estimate 432.33. And then if we went to 0.0, that estimate, there's that estimate time 10. By the way, if you wanted to go much smaller than that, let's say you weren't satisfied with the error and you're like, I need to go 0.001. The issue that you'll have with technology like this is it can't display that far down. Here it stops at time 1. It can only show about 1,001 rows, and we've maxed out. It's like, well, how do I go to time 10 now? I've only been able to get it to time 1. Well, the one way you could do this is plug in this as your initial condition, 1 and 90.63462, and kind of do this in steps. Not like step size, but in steps. And now change your initial point to be 1, comma, what it is at time 1, and submit that. And that, notice, will just generate now from 1 to 2. And then you can grab your time 2 value, plug that in for the new y value, time 2 for that corresponding point, submit that, and you can see that it'll just kind of continue going. So if you wanted to go with a much smaller step size and have this like visual type of software, you may just have to have multiple initial conditions, one for each unit of time. And there's our full analysis of Euler's, improved Euler's, and RK4. And from here on out, we're pretty much going to stick with RK4 because it's better.